Okay, in this lecture, I want to go over how to solve Laplace's equation in 2D and 3D. Later in this chapter, we'll learn some techniques to do it analytically. At this point, I just want you guys to have a conceptual understanding of it. And actually, I think it helps to learn how it's done numerically in order to get that conceptual understanding. So we're going to focus on that, and I'll show you some code in a little bit. Okay, so let's think about 2D first. Okay, so in 2D, now I'm going to write these as partial derivatives, and that's because now v can depend on, in 2 dimensions here, we're going to assume it depends on x and y. Of course, it could depend on y and z or x and z. It doesn't really matter. Okay, but now we're going to say the potential that could potentially vary in 3 dimensions. We're just going to think about it varying in 2 dimensions, okay? So we need partial derivatives because when I take the derivative of this function here, I'm just going to do it with respect to x when I take that derivative, and then I'm just going to do it with respect to y, when I take the second derivative. Okay, so I want you to note that in 1 dimension, right, we had our solution to Laplace's equation, and it was kind of boring. It just looked like a line, okay? But I want you to think about it. If I wanted to know the potential at this point here, so I want to know the potential there, right? I could take some measurements of the potential, right, at 2 points that are evenly spaced in front and below it. We'll say that's some delta x. So on 2 points of either side in this 1 dimension, and I would find, right, that v is the average. Okay, so if I called this, I'm going to call this v sub I, and I'm going to call this, let's see, maybe I'll call this, I'll call this one just v1 and this one v2. Then v in the middle would be equal to, right, just v1 plus v2 divided by 2. Okay, not hard to see. This is just the average of these 2 points. Okay, and that's what makes a straight line. All right, let's think about how to generalize this in 2 dimensions, this kind of behavior. And by the way, this kind of averaging, the fact that this potential is the average of the potential on either side, that's what creates this really boring kind of featureless thing, right? If there was a bump here in my potential, imagine a bump, right? At the top of that bump, there's no way that potential could be the average of the values on either side because it's greater than the values on either side. Same would be true if there was a dip, okay? Or if there was any kind of waviness. The only way that this can be true is if this function is a straight line. Okay, so this is one way we get to the most boring solution, is this fact that the potential here at this point is an average of the potentials around it. That kind of relaxation into this most boring state is what needs to happen in order to satisfy Laplace's equation here. Okay, so let's think about that behavior in 2 dimensions. Okay, so in 2 dimensions now, instead of plotting the potential versus x, I'm just going to kind of draw, well, maybe I'll draw it like this, so it's a little bit less like a graph. And we'll do x and y. So now we're just looking down on a spatial grid here. And same thing, I'm going to pick a point up here. And I'm going to call this v. Let's call this v x sub I, y sub I. Okay. To satisfy Laplace's equation, this v here is still the average of the points around it. So again, I'm trying to think about maybe a numerical solution initially. We'll show some continuous solutions with Mathematica, but imagine There is some continuous solution of the potential around here, which means a smooth kind of film of solutions, but I can discretize that, which means I can cut that continuous solution down into some kind of discrete grid and say, all right, the potential in one of these grids is going to be the same, and this one is going to be the same, even though it could be different than its neighbor grid. That's kind of how I'm thinking about this here. Okay, so this is the potential at a center grid point. These are the potentials at neighboring grid points, and I can just quickly give those a label. This is going to be x sub I, y sub I plus 1. This one's going to be the potential at the same x, but at a lower y, so that's going to be x sub y minus 1. Zoom in here. This is going to be v sub x at I plus 1. Y sub I, and this over here would be v sub x sub I minus 1, y sub I. So I'm using those indexes to indicate where these yellow points are relative to my middle point. Okay, so my potential at that middle point would be equal to the average of the potentials at all of those surrounding points. Okay, so and hopefully I don't have to write this whole thing out for you guys to understand it. You might want to write, I'm being a little lazy here, but you're going to add all 4 of these. You might want to write it out in your own notes because you might look at it later and try to remember what the heck's going on and not be able to realize it if you don't write it all the way out. But basically I'm taking the average of these 4 points instead of just 2, and that's how I solve for the potential of that middle point. Okay, in either case, the fact that V is an average of surrounding points. I like to skip letters here. Over here. Okay, again, tells you that it's going to be a smooth, it's going to produce a boring or a smooth solution, and that there cannot be any max or mins. Okay, there can be no max or mins. And this is true for, again, just Laplace's equation. But imagine here, okay, if this was a max, there's no way it could be the average of these points right here. Okay, so let's take a little break and actually look at a computational solution for solving Laplace's equation. And this, again, would be a normal way to do it on a computer. And what it's called is the method of relaxation. I'm actually going to switch over to MATLAB. Okay, this is the program that I'm going to use to help you guys understand the numerical technique for solving Laplace's equation, which I think helps you understand why the solutions have the form that they do, even when you solve them analytically. In this program, again, we're solving Laplace's equation, so we're assuming the Laplacian of the potential is equal to 0. We have to give it a set of boundary conditions. In this case, I'm going to come up with 2 different sets. You can either do border values, or that's not spelled right, border values, or a two-plate capacitor. Okay, I'm just starting off by clearing all of the workspace, closing all the figures. This is just a bool or a string that tells me whether or not I want to run the program in the mode where it solves the 2-plate capacitor or not. This initializes a grid to solve for the voltage values on. And then again, down here, what we're doing is we're solving for some of the boundary values. Okay, so I'm going to ignore this for now. This runs if I have this capacitor string equal to yes. In this case, it's no. So it's going to skip this code. I'll come back and talk about it later. It's going to come down here and run the code below the else statement. And what this code is doing is it's just taking this initial 2-dimensional array of zeros, which is what I've initialized V, the variable that's going to store the potential, and it's setting all of the y equals 0 values to 10. Okay, so at one of the walls, I'm setting the potential at 10. and all of the rest of the walls, the potential is equal to 0. So I can go ahead and run this and just show you what that looks like. Takes a second, and I'll show you why in a second. Okay, but here, I'm going to get rid of this. Here is how it's initially set up. Okay, and again, this is not the solution to Laplace's equation. This is how we are initially setting up this numerical solution. So it's 0 everywhere in this two-dimensional grid, but just right here at y equals 0, I've set the potential equal to 10. Okay. So if I go through here, this again, that's just producing the figure that I just showed you. Actually, I don't need this n anymore. Got rid of that. The way that I'm having this set up, we're going to use something called the relaxation method. And how that works is I'm going to replace the values of this potential grid with the average of the surrounding points. And I'm going to keep doing this until it relaxes to the real solution. Okay, so when I run this, you guys are going to see a movie of it relaxing. This is not how the potential is changing with time. This is our numerical technique that's evolving. And eventually, if I keep replacing these values with the average of the surrounding points, eventually it's going to relax to a continuous function that actually satisfies Laplace's equation. So this numerical technique, it's using a method called relaxation to find the true solution. So I'm going to run this while loop until the change of the new solution of the potential is only a little bit different, okay, than the old solution. Once there's not much change between iterations, then I'm kind of confident that we found a good numerical solution for Laplace's equation. Okay, so this first bit is storing the old values to compare. Every time I go through this while loop, now I've got a nested for loop here. And the nested for loop, it goes down to here, is going through each point here in x and y space, except where we're skipping the boundary points because I want to keep those at a set potential. It's like they're hooked up to ground or a battery. So I'm going to keep these at the values they initially were set at, but the interior points, I'm going to go through and I'm going to replace each point with an average of the surrounding points. Okay, that's what this line does. And then if I have it in capacitor mode, I have to preserve the voltage essentially on the capacitor plate. So that's what this does. But right now I'm not running this code here. So we can ignore that. This down here is just making a plot so you can actually see an animation of that relaxation method working. Let me just do something funky. Nope. Here, I'm just calculating that change variable. I'm saying what is the percent difference between the old solution for the potential and the new one. Once that's small enough, I'm going to quit running the loop. And then here, I just have some plot commands for the final solution. Then I replay that movie. So let's go ahead and let this thing run. Okay. So here I can actually see an animation of this numerical technique working again. This is not how the potential is changing with time. This is just that relaxation method, eventually finding the true solution. This side of my boundary says the potential is being held to 10 volts or something like that. Maybe it's plugged into a battery. All of the other walls in 2D space are being held to 0 volts. It's coming up with the most boring way to basically stretch fabric over these boundaries. So it's going to be a smooth continuous function, no maxima, no minima. Okay, and it's going to relax to that solution. This is just showing you a movie of what we just did a couple of times. It's kind of funky the way it came out. Okay. But again, it's important to remember this is not how a potential is changing with time. This is just showing you the numerical technique working. I'm going to get rid of that. Okay, and then here we're left with two figures kind of just showing what that looks like. So here is just the end result. So this is a solution for the potential for those particular boundary conditions. And again, I could go in there and easily change the boundary conditions to get something more complex than this for my solution. I could maybe do that next just as an example. Okay, but that's pretty boring and featureless. This is just looking from above, or instead of showing the potential with a height here in Z space, I'm showing potential with the color contour. So these two things are showing the same type of data, just two different ways. So let's just make that more fun. and solve it again. Let's go back here and change the code a little bit. I'm going to go up and instead of just setting the potential to be equal to some fixed number of 10, I'll let it equal something sinusoidal. So how about something like that? Okay, so now it'll have a little bit of waviness at the border. And I don't know, maybe at the other side here, I'll have it be equal to 2 or something like that. Okay, let's go ahead and let the program solve that particular configuration with those boundary conditions. Okay, here again, you can see it's using that relaxation method to find the smoothest, most boring, featureless contour that can fit those particular boundary conditions. Here you can see the waviness that I've initialized on the x equals 0 line here. And then over here, I've said that the potential has to be equal to 2. On the sides, the potential has to be equal to 0, so that's fixed. Okay, and it's basically just smoothing a sheet to fit those boundary conditions and coming up with a solution. Okay, and this is a true solution to Laplace's equation. Okay, there's the movie. That's coming up pretty freaky. And then here's just two different graphics showing that final solution. This is the one looking at the solution from above, showing a contour of the solution. And here, this is the solution showing a two-dimensional surface where the height is representing the potential. Okay, and again, I could go back in here and play this game as much as I want. You guys can download this program and change it to come up with some interesting solutions. But I wanted to do one more fun one. And let's see, this is kind of coming out weird anyways. I wanted to show you what the solution is when you do a capacitor. Okay, so go ahead and let this run and then explain it. Okay, what I've added here is now I'm setting the voltage equal to some values at boundaries in between my space here. Actually, I'll probably end up rerunning it. But this is basically what it looks like. It's still going to be set to 0 at the boundary points. I'm still not resetting those values, but I'm also setting the voltage either equal to 1 or -1 along these bars here. And in fact, just to make this a little bit more interesting, with the axes limits, I'll make these a little higher. Okay, here we can watch it evolve as it's running. And again, it's using that relaxation method to find that solution to Laplace's equation that satisfies the boundaries where now we're including the fact that we're setting certain regions interior to our simulation equal to a particular voltage. Okay, here's our final solution. We can take a look at it and see if it looks like what we expect it to. Okay, here we've got our two capacitors. I can kind of rotate this around. This one's obviously at high voltage. This one's at low voltage. Sorry, our two plates that make up one capacitor. If I look at this from the side, it does show me that the voltage as we go from this high voltage capacitor to the low voltage one, it does change in a linear fashion. So this relaxation method has found the correct solution far between or in the middle of these two capacitor plates. Of course, near the edges, you can see that the solution gets a little bit more complex, but it's still the most featureless solution that you can get for this particular configuration. And this is indeed what the voltage looks like near two parallel plate capacitors. Okay, so that's kind of fun. And then again, here's our contour plot showing the same information. Okay, let's go back to the notes for a second and just think about what we can do to actually solve this analytically or by hand rather than on a computer. Okay, so a way to calculate the same kind of thing rather than on a grid of discrete points but with a continuous function would be to, in 2 dimensions, would be to calculate the potential at a point x and y by taking the average value of the potential along a circle, a distance r away. Okay, so if I take the average of the potential, remember this is like summing the potential times the length around a circle, and then if I take that divided by the length of that circle, which is 2 pi r, I will get the average potential along that circle. That's going to be equal to the potential in the middle. Okay, so again, if this is the point where I want to try the potential, to find the potential, then one way I can do that is to, in 2D, I can take the average of the potential along a circle, and it has to be centered on my points x and y. Okay, and that circle can really have any radius r. As long as it's centered, this is going to work. Okay, what about in 3D? Okay, so this is in 2D. If I want to solve for a two-dimensional potential, obviously in real life we have a lot of 3D potentials we are interested in. Okay, here it's the same idea, but we're going to average the potential along a surface of a sphere instead. Okay, so mathematically that would look like this, or I could call that V sub r. And that's going to be equal to 1 over 4 pi r squared. Okay, that's like 1 over the area times the sum of the potentials along a sphere. So I can do that by taking, the sum of the potentials times the little area elements. Okay, so here I've got potential where I want to find. That's in some middle point here in my three-dimensional coordinate system. Now, instead of surrounding that with a circle, I'm going to surround it with a sphere. Still going to have a radius of r. And now, V is an average of the potential, measured along each little patch of the surface summed up, okay? Even if I do it in 3 dimensions like this, there still can't be any maximums or minimums, within this, or else it would not be the average of the surrounding values. And this again works for any r, so I could get really close around it if I wanted to, okay? It's a little bit harder to visualize that in 3 dimension than it is in 2 dimension, but it still holds true.